Good afternoon, everyone. My name is Jiro Hirokawa from Tokyo Institute of Technology, Japan. Okay, welcome to the webinar. I'd like to start my presentation. Today's title is the two-dimensional rectangular coordinate orthogonal multiplexing antenna systems for non-far field region communication. This page shows the system configuration. So we have TX antenna in left side and RS antenna right side. And these two antennas are identical. They are waveguide slot array antennas having two-dimensional monoconverse circuits. On the top layer, we have the radiating slot array. These radiating slot array are divided into 4 subarray, 2x2 subarray. Two-dimensional monopulse circuits excite this 2x2 subarray with 4 types of orthogonal excitation as shown in this as shown in the bottom. So we have mode 1, all 4 subarray are fed in phase. And mode 2, top 2 subarray fed in positive phase, while the bottom 2 subarray fed in the negative phase. And mode 3, the left side 2 subarray are fed in positive phase, while the right side 2 subarray fed in negative phase. And mode 4, the left bottom subarray, left top subarray and bottom right subarray are fed in positive phase, while the right top subarray and left bottom subarrays are fed in negative phase. For instance, we have mode 2 excitation in the two-dimensional monopulse circuit in the TX side. This subarray makes 2 beams as shown in the center figure. And this 2 beams has the opposite polarity. Okay, the top beam has positive phase, while negative phase, bottom beam has negative beams. Then RX side, when we have the same weighting with mode 2, we can have the output only to port 2. So we have 4 types of orthogonal modes. Okay. The following the contents of my talk. At first, I talk about the introduction. So, as I explained before, okay, this is system configurations. So the radiating array are divided into 2x2 subarray. And this 2x2 subarray fed with two-dimensional monopulse circuits. Actually, these two-dimensional monopulse circuits composed of 2-stage magic T. Okay. Then these two-dimensional monopulse circuits excite 4 types of modes having two-dimensional polarity. At first, I explain the feature of this multiplexing systems in comparison with OAM. So, as you may know, okay, OAM is recently intensively discussed in the radio area. OAM transmission was originally developed in the optics, okay? And the left figure shows the wave fronts for various modes. And the middle, this is the phase distributions. From m equals 0, we have the uniform phase distribution, while for m equals plus 1, for instance, we have the 360-degree phase difference in phi direction, something like that. And we have various types of phase variation in phi directions, and also right figure shows the amplitude distributions. So this various phase front makes the conical beams, and each mode has a different beam direction. For m equals 0, okay, we have boresight. However, the other modes, we have null radiation in boresight. So as I explained before, OMM was originally developed in optics area. In optics area, fractal bandwidth is almost 0. So we don't need to consider the frequency dependence. However, recently OAM is discussed in the microwave and millimeter wave area. In the microwave and millimeter wave area, sometimes we need some wide fractal bandwidth, around 20% or more. So in this case, we have to consider the frequency dependence of this excitation. And OAM is based on the orthogonality in the cylindrical coordinates. And in the microwave and millimeter wave area, most of the study is works on the orthogonality in phi direction only in OAM. So if you consider the orthogonality in low direction, we have to treat differently in the orthogonality in the phi directions. On the other hand, our multiplexing depends on the orthogonality in the rectangular coordinate systems. So we call as rectangular coordinate orthogonality multiplexing, short is ROM. In this ROM transmissions, orthogonality based on the polarity by structural symmetry of magic T. This is magic T. So one of the key components in ROM transmissions. In magic T, we have two input, sigma ports and delta ports, and we have two output ports. So for input from the sigma port, to output port has in-phase division, while when we have the input from the delta port, to output has the alternating phase difference. Okay, so in magic T we have the symmetrical structure here. So regarding to the polarity, considering this structure symmetry, we have no frequency dependence on polarity. And this long transmission based on the orthogonality in the rectangular coordinate systems, so that we can treat equally for x and y directions. So it is easily extend from one-dimensional orthogonality to two-dimensional one. Next, I talk about the 4 multiplexing 60 centimeter CW transmission using 80 GHz band 60 by 16 slot waveguide array. This is the structure of the corporate field slot waveguide array with two-dimensional monopulse circuits. We have the radiating elements on the top layer. On the middle layer, we have the corporate field circuits. And bottom layer, we have the two-dimensional monopulse circuits. So as I said before, okay, two-dimensional monopulse circuits is a two-stage of magic T. And in the middle, we have the corporate field circuits. The right figure shows the 2x2 element subarray of subarray with end of the corporate field circuits. So each end of the field waveguide, we have the one coupling slot here. This one coupling slot excites 2x2 radiating elements, radiating slots in equal amplitude and phase. So basically, all radiating elements are fed in phase. Okay. And later we control the amplitude and phase. Sorry, amplitude and phase in corporate field circuits. Okay. So corporate field circuit is a one stage of T junctions. Amplitude taper is realized by the offset field of the T junctions, and phase difference also realized by offset field of the T junctions as well. The left figure shows the frequency simulated results of the distance dependence of the coupling coefficients. Light green results is a transmission coefficients for mode 1, where all subarray are fed in the E phase. And when the distance is short, the transmission coefficient is almost constant. In this region is near field. And when the distance, propagation distance is larger, this transmission coefficient degrades. This is far field. Here is far field. So sorry, thick green line shows the results for the mode 2 and mode 3, where two subarray are fed in positive phase and the other two subarray fed in the negative phase. Okay. And red line shows the results for the mode 4. Two subarray are fed in obliquely in oblique direction. Okay, two subarray in oblique direction are fed in positive phase, and the other two subarray are fed in the negative phase. And bottom figure shows the beam shape depending on the mode excitations. Okay, so mode 1 has both side beams, okay? While mode 2 and mode 3 has two beams. They are separated, okay? And mode 4 has 4 wheels. Other than mode 1, mode 2 and mode 3 and mode 4 has null wheel in bore side. Please note this. And we have the measurements of the transmission as shown in this picture. Okay. So this is the frequency. Sorry. The right figure shows the frequency dependence of the transmission coefficients for the distance of the 41 centimeter for the 60 by 60 element array at the 78.5 gigahertz. So as regarding to the frequency dependence, okay, this is a flat dependence, considering the component feed circuits. Okay, component feed circuits gives very wide bandwidth. We can cover from the 70 to 86 gigahertz full E-band. Okay. Okay, I have some question about the difference between the non-far field and near field. Okay, okay. We can generally, okay, we can deal with the near field and Fresnel region and far field. So we want to deal with not only the near field around here, but also we try to realize some kind of transition area in Fresnel region. Okay, transition area from near field to far field. So we try to deal with, okay, both near field and Fresnel region. Okay, so we call as non-far field region. Okay, so we don't deal with far field. Okay, here. So this is the measured transmission coefficients. Okay. The right top figure shows the mode 1. Okay. And dashed line is the simulated results. And solid one is the sorry. Dashed one is the simulated results. Sorry. Dashed one is the simulated results, and solid one is measured results. Okay. In principle, okay, in theory, okay, we have the perfect orthogonality. So in principle, okay, undesired coupling is 0 in simulation. Of course, in actual measurement, we have the some small coupling. Okay. In this case, okay, we have about 15 dB isolation only. So because this isolation is slightly low, because in this measurement we use the beam alignments by hand. So if you apply more accurate alignment, we can get better isolation. And the right top shows the result for the mode 2, and left bottom shows the result for the mode 3. And the right bottom figure shows the result for the mode 4. Anyway, we have the for all modes, okay, case, we have the fairly good agreement between the measurement and simulation for the desired mode. This figure shows the propagation distance dependence of normalized channel capacity. In my presentation, normal capacity gain is defined as according to this equation. Okay. So of course, there are various definitions, okay, for the gain. But in this talk, I define this according to this equation. And we also we assume each of four subarray is fed in equal power. Okay. Of course, okay. This also we can fed different power for each subarray. Okay, depending on the performance. But here, okay, in order to show just feasibility, okay, we assume each of four subarray is fed in equal power. And we assume also the signal noise ratio is 30 dB. Almost similar to the cross polarization level. Okay. According to this definition, okay, of course, the near field region, all radiated power can be captured by RX side. So this capacity gain is 4. But when the propagation distance is longer, this capacity gain decreases, okay? Especially in the far field, okay? Region, okay, this capacity gain integrates for longer distance. For the distance of 0.4 meter, in our case, we can estimate the 3.5, okay, in simulation. And also the alignment is also quite important. So this is the simulated results, the effects of the misalignments. The left top figure shows the desired transmission, and the other three plots show the isolation level. Okay. So the black line shows the counter for 50 dB isolations. For instance, the S61, okay, mode 2 has the two beam in the vertical directions. So we have the severe alignments in vertical directions. Okay. So next, I talk about the transmission enhancement by optimizing the excitations. So as I said before, except the mode 1, we have null beam in both sides. So we have large beam separation for longer distance. So when we have the uniform aperture phase distribution, wave front towards outwards, okay, beam are separated. So in order to compensate this beam separation, we introduce tapered aperture phase distribution over the aperture, okay, like this, inward direction. So wave fronts, okay, go to the right direction at some difference. So we optimize the amplitude distribution and phase distribution for the distance of the 0.4 meter distance. Okay, for each desired distance, we have to apply the different excitation coefficients. So in this case, we realize for the 0.4 meter, okay, for 16 by 16 element array. And also in this simulation results, we use the 60 gigahertz band, okay. And the right top figure shows the propagation distance dependence as a function, propagation distance dependence of transmission. And dashed line shows the result for the uniform excitation case, while the solid line shows the results for the optimized excitation case for the distance of 0.4 meter. Okay, so we have the larger transmission, especially for mode 4, okay, at a distance of 0.4. Similar excitation, okay, considering the beam shape of the mode 4, okay, in the amplitude distribution. And this is the propagation distance of the capacity gain. Okay, we use the same definition. Okay, and dotted line, sorry, black dash line shows the capacity gain for the uniform excitation, while the solid line shows results for the optimized excitation. We have the, I don't know, 10% enhancement in for the 0.4 meter distance. And blue line shows the measured results. Okay, so measured results has a slight have a ripple. Okay, this ripple caused by the multiple reflection between the TX and RX antenna. So this multiple regression it caused the problem. So it should be suppressed by the future study. Okay, but anyway, okay, measured capacity gain is larger than the uniform excitation case. Next, I talk about the 8 multiplexing 20 centimeter CW transmission using 60 GHz band 16 by 16 slot dual polarized waveguide slot antenna. So by applying the dual polarization, degree of multiplexing can be double. Okay. So the left top figure shows the configuration of the dual polarized antenna. Top layer, we have the radiating elements. So the radiating elements are shared for both polarization. On the other hand, feeding circuits, both component feed and two-dimensional circuits is differently for as for the feed circuits, okay, is introduced for each polarization, okay. So we have introduced, okay, feed circuit and monopole circuit for both each polarization, each of both polarization, okay. And this is the measured field distributions. Okay, the center figure shows the amplitude distribution at the design frequency. We can achieve the uniform excitation. Okay, in this case, and the bottom figure shows the phase distribution. Okay, in mode 1, okay, all subarray are fed in the E phase. And mode 2 and mode 3 has the 180-degree phase difference. Vertical direction for mode 2 and horizontal direction for mode 3 and oblique direction for mode 4. And left figure shows the at the picture on the top and left bottom figure shows the measurement setup. Okay, we control the distance between TX and RX antenna. And the left top figure, right top figure shows the frequency dependence of the reflections. VSWR less than 2 for 4 gigahertz band, 7% bandwidth. And the right bottom figure shows the frequency dependence of the isolation. Over the 7% bandwidth, the isolation level more than 22 dB. Okay. And this the left figure shows the major transition for mode 1. Okay. The left top figure shows the distance dependence. Okay. Up to the 0.2 meter, okay, the transmission is almost constant. So the S11 is the desired one, okay? And the other color line shows the isolation level, okay? In this case, we have the alignment by mechanically, so we have better isolation about 22, more than 22 dB, okay? And also, of course, the frequency dependence are also very flat, considering the wideband characteristics of corporate fee circuits. And this figure shows the capacity gain performance, okay? And the definition of the capacity gain for dual polarization case given according to this equation, okay? And we consider the signal, we assume the signal noise ratio is 30 dB, okay? So, which is closely related to the PT over N total. PT is transmission power, and N total is noise power, total noise power, okay? And we confirm the measured XPD is 35 dB, okay? So, which is related to the ratio PT over N cross polarization, okay, is 35 dB, okay. And also, we consider the interference, isolation, okay. Isolation, as I showed before, okay, about 22 and 24 dB over the operation bandwidths, okay. So we consider, we assume NT over N cross polarization is 35 dB, and we PT over N total is 24 or 22. Okay. This simulated value of the capacity gain has good agreement to measured capacity gain. Okay, measured capacity gain is shown by red lines. Okay, by using this P over N. Okay, we have a good agreement with measurements. Next, I talk about the distance dependence by optimized excitation and subarray spacing. So basically, okay, this is a non-far field region communication. So basically the propagation distance depends on the antenna size. So of course, if we increase the size of the antenna, we can increase the propagation distance. And so we investigate propagation distance increase, introducing the subspacing, subarray spacing, okay, as shown in this figure, okay. So this is just the simulated results. Subarray size is A, and subarray spacing, center to center, is large D. We assume elements as using infinitesimal magnetic dipole. So we change the value of the subarray spacing ratio D over A, and we also change of the element spacing. We define, we estimate the transmission according to this equation. Numerator is a square of RX antenna receiving power, and denominator is a product of TX antenna radiating power with RX antenna radiation available power. Okay, so we consider the mutual coupling between elements. Okay, and the normalized capacity gain is defined according to this equation. Numerator is the capacity gain for optimized excitation having spacing between subarray, while denominator is a capacity gain for the uniform excitation having no space between subarray. This is the dependence of element spacing. Horizontal axis is the element spacing, and the blue vertical line shows the enhancement ratio. And so we change the element spacing, then we change the subarray spacing ratio. Then we estimate the normalized capacity gain and propagation. Also, we give the propagation distance to maximize the normalized capacity gain. Okay. So the normalized capacity gain is obtained for, is maximized for the element spacing is 0.865 wavelengths here. Okay. In this case, the subarray spacing ratio value is about 1.5. And the propagation distance is about 200 wavelengths. This results for the 60 by 60 elements. However, when the element spacing is larger than 0.9, okay, normalized capacity gain is decreased. So we have no effects, okay, introducing subarray spacing for the element spacing larger than 0.9 wavelengths. And this is the dependence of number of elements, okay. The left figure shows the element spacing for the 0.9 in wavelengths, while the right figure shows the results for the element spacing for the 0.83 wavelengths. Okay. For the element spacing of 0.9 wavelengths, okay, we can increase propagation distance and normalized capacity gain due to the increase of the number of elements. On the other hand, for the element spacing of 0.83 wavelengths. Okay. Normalized capacity gain is almost constant, independent of number of elements. Only the propagation distance increases for the number of elements. Finally, I will explain about the two multiplexing 40 centimeter QPSK transmission using 60 GHz band 16 by 16 slot waveguide array. This is a measurement setup. Okay. We use the 60 by 60 elements antenna. And the propagation distance between TX and RX antenna is 400 millimeter. Okay. And we used RF module having transmission power of minus 5.6 dBm at the WR15 waveguide port. And the maximum ratio, maximum transmission ratio is 3.22 gigabps for QPSK per channel, 2.16 gigahertz bandwidth. This RF module is provided by Japan Radio Company and Sony corporations. And at first, I will show you the frequency dependence of the CW transmission. Okay. The left top figure shows the TX mode 1. Left top, right top is for mode 2, and left bottom is for mode 3, and right bottom for the mode 4. And the bottom figure shows, I explained before, the beam shape. So we can find the good combination having high isolation. So mode 1 and mode 4 has good isolation. Okay, mode 1 has Boresight beam, and mode 4 has 4 beams. Okay, this combination we have good isolation, more than around 25 or 30 dB. Okay, and mode 2 has the 2 beam in the vertical direction, and mode 3 has 2 beam in horizontal direction. Okay, this combination, mode 2 and mode 3 has larger isolation, also 25 or 30 dB, okay, isolation. Okay, so we found, okay, depending on the shape of the beams, okay, we have the good combination. And this is the frequency dependence of the eigenvalue of for 2 modes, okay? For each combination of the 2 modes, we have the larger eigenvalue and constant value for depending on the reflecting the wideband characteristics. And we have the 2 multiplexing measurements. Both RX and TX antenna are actually 4 ports in total, but currently we use 2 ports of 4. So the other 2 ports are terminated by rods, okay? And port 2 is a desired mode. So this signal level controlled by fixed attenuator. And port 3 is interference mode, okay? So this interference mode also controlled by another attenuator, okay? So anyway, we control both signal and interference level, both, okay? And the right figure shows the bit error rate as a function of the ratio of the port 3 interference over signal ratio, port 2, okay? So when increase the this interference level, of course, interference, horizontal axis is the level of the interference over signal level. And solid color line shows the bar for interference side, okay? When we change the attenuation level of the signal level, attenuator in the desired mode. And dashed line show the results of the bar of desired mode 2, okay? So we can find the range of the interference level over the signal, okay, to realize the bar less than 0.001, okay. And this is the tables summarize the results, okay. This table shows the range of the input power ratio for bar less than 0.001, okay. So as I said before, okay, we have a good combination of modes, okay. Mode 1 and mode 4 has one of the good combination. So mode 1 and mode 4 combination, right top here and left top here. In this case, we can have wider range of the input power ratio. Similarly, mode 2 and mode 3 has another good combination, okay? So for mode 2 and mode 3 case also, we have wide range of the input power ratio for bar less than 0.001. Okay, so anyway, good combination of beam shape, okay, gives wider range of the input power ratio. So in conclusion, I have shown you the recent results of the two-dimensional rectangular coordinate orthogonal antenna systems for non-far field region communication. Thank you very much. So now I want to receive chat your question by chat. Please put in chat or Q&A. I have two questions. If the center of opposing antenna shifted, will the strength of the received signal field change? What application can this antenna be applied to? Okay. So the first question. Okay, first question is related to this one. Okay, alignments. Okay, so the left top here shows the transmission coefficients of desired mode when we have the misalignment in simulation. Okay, so this is the 80 GHz band operation using 60 by 16 elements. Okay, So this counter is every 1 dB. So you can imagine the how much alignment you can allow, okay, according to this results. And what application can, second question is what application? Frankly speaking, okay, I don't have a specific application yet. Anyway, of course, it's quite difficult for the far field region application. So anyway, the propagation distance is limited, considering the antenna size. Question. Do you have any other questions? Okay, I will explain the magic T principle. Okay. So magic T is a important components of the microwave area. Okay. So magic T has the okay, 2 input ports. Okay, and 2 output ports. Okay, magic T is a combination of H plane dividing T junction and E plane dividing T junctions. Okay, so sigma side. Okay, this is the H plane division. So to port 3 and to port 4, we have the in phase power dividing. While we have input from delta port. In this case, we have the E-plane dividing. So output to port 3 and port 4 in the 180-degree phase difference output. And between the sigma port and delta port, we have high isolation, considering the field distribution. So I think, yeah, more detail about the operation of the magic T can be found in the textbook in the microwaves. Okay, if we do not have any more questions, we'd like to close this webinar. Thank you very much for your attendance. Thank you very much.